Okay, now we consider two examples to understand hypothesis testing and confidence interval for the generalized t-distribution. Suppose that you are provided with such a problem that y has a normal distribution with this mean and the covariance sigma square identity. Indeed, this is actually the design. So it is x, and this is the b, and this is the mean of our observations. So the mean of the first element of y, the second element of y, the first element, the second element, the third element, you can easily obtain this way. So the expected value of y is xb, and the variance covariance matrix, which I write it as variance, or you can write it as covariance here because it's a vector, is sigma square identity matrix. And consider the linear function q prime b. We further assume that q has 4 elements, q1, q2, q3, and q4. So we consider a linear function of the parameters, and we want to conduct hypothesis testing. Remember, according to the Gauss-Markov theorem, the best estimator is of the q prime b is the q prime b hat, and the variance can be obtained in this formula, but assuming the independency. So we must show in one hand that mu hat is independent of alpha hat, is independent of beta hat, independent of gamma hat. If this is the case, then you can write the variance of the q prime b hat as the summation of these 4 elements. But for this, we indeed need to compute the covariance of b hat, because the covariance of q prime b hat is q prime covariance of b hat q. I have q, and if I find the covariance of b hat, everything is solved. But for the covariance of b hat, you know that it's x prime x generalized inverse sigma square. Now the question is how we can calculate the generalized inverse of x prime x. First of all, we know that q prime b is estimable if q2 is equal to q3. You can construct the augmented matrix. You can construct the augmented matrix as q prime x, and then the rank of q prime x must be equal to the rank of x. And then you will find that, okay, the elements of q must satisfy this regularity condition. q2 must be equal to q3. Now, using the fact that you can write the best estimator as x prime x generalized inverse x prime y, which x prime x is, this is the design x, so you can easily compute x prime x. The x prime x is given by this matrix, and x prime y is also given by this matrix. This vector. It is of course a matrix of dimension 4 times 1, but we call it vector better. Which the second and third elements are the same, so I can use the abbreviation capital Y1, Y2 for the second, Y2 for the third, and Y3 for the fourth element. Now we know that this is the x prime y, and I can write x prime y as x prime times y. So solving it will easily give you the generalized inverse of x prime x. So you can easily obtain the generalized inverse. And now we have the generalized inverse, and you see if we assume the normality assumption, then since the covariances of off diagonals, or better said, the elements of off diagonal are 0, we can find that the estimators are independent. So you can come back to this formula and accept it. Let me just highlight it. You can accept this equality. You can accept it. Okay, now, but specifically, the covariance of b hat is then given by x prime x generalized inverse sigma square. And as I said, under normality assumption, we have the independency of the estimators. Furthermore, I can write the variance of linear functions of the estimators, the q prime b hat, as the variance of summation of these elements, because here we've obtained them, so I use them here, and it is simply given by this formula. Now let's go to the hypothesis testing. I want to check this null hypothesis, whether it's true or not, or whether it's accepted or rejected based on the data. But for the theory, we need to construct a test statistic. For that, first of all, note that the q prime b must be equal to gamma, and here in this case q is given by this column vector 0, 0, 0, 1, because the last element is gamma. If I come back to b, you will see here that, okay, in b the last element is gamma. So in order to get q prime b equal to gamma, you must pick q to be this column vector. And simply, the variance of gamma hat is 1/8 sigma square. Now recall, in order to construct the test statistic, you have the best estimator, which is actually q prime b hat here. This is q prime b hat, minus q prime b, which here it is gamma, and we assume that under the null hypothesis it is equal to 0. So q prime b hat is gamma hat. Here is gamma hat minus 0 under the null hypothesis, and then divided by 1/8 MSE. The sigma squares vanishes, and we can easily get this t prime t. So this is the test statistic for testing this null hypothesis, and also to construct a 1 minus epsilon confidence interval for this linear function of parameters. First of all, we have the estimators according to this formula, which we obtain the estimators for the parameters. We can find the estimators for this linear function of parameters. This linear function indeed obtained by q prime b, which q is given by 0, 1, 1, minus 1. So you can obtain this way. And you also need the variance for the denominator. So the variance can be obtained easily based on the formula that we have here. And finally, the 1 minus epsilon confidence interval for this linear function is given by this formula. Remember, the test statistics has t distribution with 5 degrees of freedom, 8 minus 3. Here we have 3 parameters and 8 in general. So the number of observations, if you remember, it is n minus r. So 8 minus 3 gives 5, and you can construct the confidence interval in this way based on the quantile of the t distribution. Once again, if the variance is this guy, remember in the denominator you always take square root. So the square root of 1/4 is half here. So half comes from the square root of 1/4. Another example, suppose that you provided with 2 independent samples. The first sample and 1 observations from this normal distribution, and 2 observations from this normal distribution. Both samples are independent from each other. We augment all the samples, so we have this n1 observations here and n2 observations here in order to construct our y vector. And the expected value is given by x beta, and in or b, not a difference. If you, most of the time I call it beta according to the common notation of regression modeling, but since sometimes we have parameter beta, so it is better if we use b. Okay, in this case I can write it as a column vector of ones of dimension n1, and then the zero vector, zero of zeros of dimension n1, again zero vector dimension n2, and column vector dimension n2. So this is the design matrix. This is x, your x, and then you have mu1, mu2, and so this is the b. So the expected value is actually xb. Once again, we have this problem under normality assumption. We also know that the rank of x is equal to 2 because we have two independent columns. We must keep in mind. Okay, now in order to compute the estimators, the MSE, and constructing the test, we need to compute first of all x prime x, and simply if you transpose x and multiply by x, pre-multiply by x, then you have 1n1 transpose 1n1 dimension, 0 0 1 dimension n2 transpose 1 dimension n2. So this is your x prime x, and also for the normal equation we need x prime y, which is 1 n1 transpose y, 1 n2 transpose y, and it is indeed the sum of observations for the first sample. So j varies from 1 to n1, and the second element of x prime y is the sum of elements of the second sample. Sorry, I must write it the second sample. Sum of y2j from 1 to n2. Once again, remember the normality assumption. So you can of course construct b hat. Let's first compute b hat. We know that b hat is x prime x generalized inverse x prime y. But since x prime x is a diagonal matrix, if you compute it, it is equal to n1, and if you compute this element, it is equal to n2. Since it's a diagonal matrix, so it's invertible according to the properties of generalized inverse, so I can write it as x prime x inverse x prime y. And it's once again it's a diagonal matrix, so you only need to consider the reciprocal for the diagonal entries. So it is 1 over n1, 1 over n2 for the diagonal entries, and then we have the x prime y, the summation y1j, summation y2j, n2, n1, and simply it gives you, if you do the computation, it is y bar 1, y bar 2. That's why here we have the mu hat I is equal to y bar I. So mu hat 1 is equal to y bar 1, and mu hat 2 is equal to y bar 2. Remember here, this guy is actually mu hat 1, mu hat 2. Okay. The next step is to compute the SSE. For the computation of SSE, let's write the formula. It is, of course, the sum of the squares of all the elements, all observations, minus b hat x prime y. The sum of all elements, we have two summations over I and j power 2. Let's say I and j, and then the sorry, it must be transpose. So b hat transpose x hat x prime y x prime y. So I write it here minus the y, the b hat. We computed the b hat as y y bar y bar 1, y bar 2. So it is y, the transpose is y bar 1, y bar 2. And then the x prime y, which we already computed as n y bar 1, n y bar 2. If you do this, you can then write it as this formula that I have in my notes. So I can write it in this way if you do this multiplication here. And you can easily write it in one formula. So this is the SSE, the formula for the SSE. So if you have the observations, the mean of the first sample and the mean of the second sample, you can easily compute the SSE. Remember, here we have two independent samples. The first one has dimension n1, the second one has dimension n2. Next step, we need to compute MSE, which is given by this formula. Again, it is n minus the rank. The total sample is n1 plus n2, and the rank we already computed is equal to 2, so it's n minus 2. The next step, we need to compute the variance. Since these are, y bar 1 is independent of y bar 2, the variance is the variance of y bar 1 plus the variance of y bar 2, and it is simply obtained by this formula. So this from here to here, I use the independency between two samples. Now we can easily construct the test statistic. First of all, this is a common test for two sample problems. For two samples problem, you want to check whether the mean of the first sample is equal to the mean of the second sample. Let's say the blood pressure of the girls to the blood pressure of the men or boys. We want to check that. Okay, I need first to write it as q prime b. Here, or b is mu1, mu2, and we need to find the q. In order to find q, I can write it as mu1 minus mu2 equal to 0. So I can assume that m, which here I recall the formula, or the q prime b, which we can write it as m according to the previous videos. The m is equal to 0, and here for the q, I have this q. I can conclude that the q is 1 minus 1. So this is your q, and we want to check this null hypothesis. Q prime b is equal to m. M here is 0, as I said. So this is equal to 0, and this is equal actually to mu1 minus mu2. So you can easily construct the test statistics. Once again, I'll write the test statistics. It must be q prime b hat minus m divided by the estimation of the variance of q prime b, which you can write it as mu hat 1 minus mu hat 2. M is equal to 0, and then the estimation of the variance of y bar 1 minus y bar 2. And we have all the elements, and you can see that, okay, this is the test statistics in order to test this null hypothesis. The next one is the generalization of the t distribution to let's say several sets. So here we consider the generalized f test. For the generalized f test, I assume that, okay, remember previously for the generalized t we had t prime y. T was a vector. Here we have a matrix t. So t prime y is actually let's say s sets. We want to consider the hypothesis for s sets. This is the first one, t2 prime y up to ts prime y. And also q prime b is from the generalized t is changed to capital Q prime b, which again we have S sets for the functions of parameters, Q2 prime B up to Qs prime B. The story is the same. We want to conduct hypothesis testing and construct confidence interval, but here for the S sets. So if you remember from previous videos, let me write it. First of all, we have the error space, which is generated by the columns of E, generated by the columns of E, which is of dimension n times n minus r. And here we have A prime y, which is now consider the normal distribution for that, and the mean is equal to 0. In previous video we've shown that, and the variance covariance matrix is equal to sigma square A prime A. Once again, we assume that y has normal distribution with mean xb and variance covariance matrix sigma square identity matrix. Now according to the lemmas that we said in previous videos, I can standardize it, and I can write it as A prime y, this covariance matrix, the root of inverse. It has then normal distribution 0 identity matrix, and then you can construct chi-square distribution, so you can write it as y prime. Let's say it is z, and then you can consider the distribution of z prime z. For the distribution of z prime z, I will get the chi-square distribution, but let's write it here, expand the elements. It is then A prime E inverse A prime y, and for a moment I have sigma square in the denominator because it is sigma square here, so I take it out. I can write it as sigma chi-square distribution with n minus r degrees of freedom. Another thing, if you want to construct the test statistics for testing this null hypothesis, we also need the distribution of T prime y, which you can see it's given by the normal distribution with this mean and this variance covariance matrix. But for construction of the test statistics, I must show that it is independent of SSE. Once again, let's recall the covariance of T prime y and E prime y. You can easily write it as T prime E sigma square, which is equal to 0, because T is in VR and E is in VE, so they are mutually orthogonal. So I can conclude that T prime y is independent of E prime y, and consequently T prime y is independent of SSE. So then once again I can standardize it exactly this way. What I did for E prime y, I can do exactly for T prime y, and I can then standardize it. I can take it out. I can take this part out under the null hypothesis. Remember, it's equal to 0. And then this statistic has chi-square distribution, or we can say that y prime T prime T inverse T prime y has sigma square chi-square distribution with s degrees of freedom, which we call it the sum square of hypothesis. Once again, why sum square of hypothesis? Because it's under the null hypothesis, so we assume that Q prime B is equal to 0. So under the null hypothesis, I can construct the test statistics in this way, as the SSH divided by S and SSE divided by degrees of freedom n minus r. But why this structure? Recall that if I have U distributed according to chi-square with p degrees of freedom, and V distributed according to chi-square with, let's say, Q degrees of freedom. And if they are independent, then I can conclude that if I define the W variable as U divided by P and V divided by Q, then it has the Fisher distribution with P and Q degrees of freedom. The P is for the numerator degrees of freedom, and Q is the degrees of freedom for the denominator. So I can use the same theory here and construct the test statistics in this way. So the test statistics is given by this F, and it has Fisher distribution with S and n minus r degrees of freedom. So F has F distribution with S and n minus r degrees of freedom. But under this null hypothesis, we have Vs as a subspace of Vr. So the space that I construct under this null hypothesis is a subspace of Vr, your regression space. And in the next video, I will explain why it happens. I just want to stop it to make it short. The problem here, or the question better say here, how can we compute SSH? Huh? This is now the question. How I can compute SSH? We can compute SSH directly, or we can compute SSH with another theory, which I call it the principle of conditional error. So the estimation, or better say the computation, is in two directions. We directly compute the SSH, and we can also compute it indirectly, better say using a principle of conditional error. In the next video, I will explain about the principle of conditional error, and I will show why Vs is a subspace of Vr, and the geographical representation of that. Thank you.